have gone through the introduction to our lab number 3, and then we have gone over the lab manual and how this experiment will be done, and what kind of information we can collect. So in the eCampus, I'm going to post the results of the flash vaporization, differential vaporization, and the separator test, and all the liquid and gas expansion experiment data, and then you can use those to perform your lab. So to make your life easier, I have also added 2 instructions on how to complete this lab report, the analysis and the calculations. So the first one is called the experiment 4 instruction, and then experiment 4 instruction continued. So I'm going to go over those 2 files, and you can just perform exactly the same way that we discussed here and then complete your lab. So in the experiment 4 instructions, the first step is to find your initial condition. So you fill up this table, and this will be provided to you. So you know what is your cell temperature, ambient temperature, pressure, and volume. And you know the gas chromatography of the fluid at the initial condition. In the second step, I'll provide you with the bubble point pressure and the bubble point volume. These are obtained through our flash vaporization test. In the third step, I'm going to provide you with the 8 gas expansions, okay? The data associated with 8 gas expansions. So when you have those 8 gas expansions, you need to generate your table of differential vaporization test, okay? So this table starts from stage 0, which is basically your bubble point, all the way to stage 8, okay? And in this table, you need to find your gas vaporization, M, which is your mass, R, universal gas constant, T, temperature, P, pressure, methane, propane, and hexane concentrations, apparent molecular weight, moles, number of moles, volume, F1, capital F, and capital E. We are going to use the capital E to calculate our BG, we use capital F to calculate our RS, and also we are going to use the CBF to calculate our BO, which I will go over it. So how to generate this table? So the first thing, so at the bubble point, so this is the start. So this is the initial condition. So you just can put the initial condition here. We don't have any gas expansion. So we go to the first row. That's the first expansion. So the gas vaporization is equal to the gas actually expanded out of your cell in cc's. Okay. So what does that mean? So whenever we drop the pressure in the cell, some gas will come out of the liquid in the cell. And then we try to send all that gas out to have the gas expansion. However, due to practicality of this problem, you will never be able to get all the gas out. Okay, so you use the pump. You pressurize. You try to send the gas out, but it's very hard to get all the gas out. So there are a small amount of gas will left in the cell. So this gas vaporization, which is equal to the gas actually expanded, is equal to the gas cell content before expansion. So how much gas you initially had in your cell. Let's say you are at the bubble point pressure, you drop the pressure by 50 psi, and you get 1.568 cc's of gas in the cell. And then minus the gas cell after the expansion. So after you try to send that 1.568 cc's, for example, gas out, you will see in the cell you will end up with having 0.002 or 0.007 cc's of gas left in the cell. So since that amount is left, you need to subtract that from the total amount of gas to be able to get the actually expanded gas. So we drop the pressure, we know how much gas we have in the cell, and then we subtract that amount from the amount that will be left in the cell after our expansions. Okay, so this is how we get the gas vaporization. Mass of gas. We measure the gas density. Okay, so the gas density using D2 is already measured for every pressure. If you multiply that by the actually gas expanded, so this is mass over volume, you are multiplying by the gas volume, then you get the mass. So this is how we are getting the mass of the gas. R is our universal gas constant. Okay, So this universal gas constant is not 10.732 anymore. You need to go to the wiki and then Wikipedia, Google, and see what is the R value associated with cubic centimeter, atmosphere, Kelvin, and mole. Okay, that becomes the actual R value. Okay, for your test. The same goes for the temperature. The atmospheric temperature, convert that in Kelvin. Okay, so 60 °F converted that to the Kelvin becomes your atmospheric temperature. And the pressure, which is basically 1 atmosphere. So for all the gas expansions, since these numbers are measured at a standard condition, R will be constant, T will be the room temperature in Kelvin, or at the standard temperature in Kelvin, constant throughout, and P will be constant 1 atmosphere throughout. So RT and P will be constant for all the 8 expansions. M, mass for every expansion, is equal to the gas density measured at that expansion times the gas vaporization, or gas actually expanded. So we have all these first parts. We have the gas vaporization, mass, RT, and P. The concentrations, so since you want to find the gas volume, that would be the gas mole fraction in gas chromatograph. So these are the gas mole fractions that you obtained at the end of every single gas expansion using the gas chromatograph. So these are the final gas chromatograph. This is when the gas is coming out to your gas vessel, and then you send it to the gas chromatograph. So the composition of gas you get at the end of every gas expansion will come here. Then you need to calculate the MA, that's apparent molecular weight of gas. So how do we calculate that? The mole fraction of every component times their molecular weight. You sum them up, divided by the molecular weight of air, which is 29. Okay, so then you get the apparent molecular weight of gas. Then you need to find the N. What is N? N is the mass over apparent molecular weight. So mass, you have it. That's the second column. Apparent molecular weight, you have it. So mass over molecular weight, apparent molecular weight gives you the N. That's number of moles. Now you need to find the V, the gas volume. So PV is equal to nRT. Pressure, you have it. N, you have it. R, you have it. And T, you have it. So you can find V. So V is equal to N RT divided by P. P is 1, and you calculate it. R is constant and T is constant. So you can find N for every gas expansion, multiply by RT and divided by 1. That's your capital V. Then F1 is the relative gas volume at the standard condition. That's the volume of gas divided by the volume at the bubble point. Okay, so we are going to normalize those. So we normalize all those volumes by the volume at the bubble point. Okay, which we found using flash vaporization test. So this is our F1, and then capital F is a cumulative relative volume of gas. So F1, capital F for the first expansion becomes equal to F1. For the second expansion becomes the F1 at the first gas expansion plus F1 at the second gas expansion. For the third gas expansion becomes F1 at the first plus the second plus third. So the capital F is simply the cumulative relative gas volume measured. Okay, so we have that column as well. And finally, to get the E, the gas expansion factor, that's the gas volume divided by gas actually expanded. So gas volume at the standard condition divided by the volume of gas at the reservoir, the gas actually expanded. So the E becomes V divided by gas vaporization. So this way we can have this whole table completed. Now that we have the E and we have the capital F, the CBF and RSIF, I already showed you how to calculate those in the previous presentation. So you can use the equations given in your syllabi, in your lab manual to calculate the rest of the parameters. Okay. And again, for your reference, how to find the CBF and solution gas oil ratio, initial solution gas oil ratio is also presented here. So in addition to this instruction, I also have the lab number 3 instructions continued. Okay, So in this one, basically what you have is the CBF. Again, it says for gas mass used 1.568 gram. That's what we found through our experiment. So the CBF we calculated, that was a constant number. That was 0.398. That was constant. The pressures start from the reservoir pressure to bubble point pressure and my 8 gas expansion. So I have that. The VB was 10.26. That's the volume at the bubble point. I have that. The volume of gas plus volume of oil, we have that value. And this is volume of gas, this is volume of oil. This is total amount of gas. The BO, the formation volume factor, requires the VO, the VO over VB. So VO, we have the volume of oil. VB, that's 10.26. So VO divided by VB, this becomes that small VO. That's a normalized VO. So normalized VO divided by the CBF, which is a constant, will give you the BO value. Okay. So, for example, for the first one, the VO over VB is equal to 0.97 divided by the CBF, which is 0.398, becomes 2.44 or 45. So this is 2.4445, depending on how you round this number. So you get the BO. And then for the RS, you have the equation in the slides or in your lab manual, which is based on the RSIF and CBF, and the BG is basically 1 over E, which you have in your slides. So if you let me just bring those one more time to make sure that we have the correct equations. Okay, so experiment 4. Okay. So the equations are given here. So BO is the small VO. That's our oil volume over volume at the volume at the bubble point divided by CBF, which is constant. RS, which is our RSIF that we calculated, that's a constant. The CBF, that's a constant. And the capital F that you just got through that column, and BG is 1 over E. So when you have all these values, then you simply can find the tables of the BG, BO as a function of BG, BO, and RS as a function of the BG, BO, and RS as a function of pressure. So at the end, what I'm going to plot the BO versus pressure, BG versus pressure, and RS versus pressure. So again, BO was a small VO, which is V over VB divided by CBF. BG was 1 over E, which we got it from the previous table. And RS was basically RSIF minus capital F divided by CBF, okay? Which again, you have all those values in the table. So in this table, you had the capital F, capital E, so 1 over E is BG. You have capital F that you can use to, here you can use to find the RS, and you can find the BO. So when you do that, then you will have the 3 graphs. You will have 3 graphs showing how the BG is changing, how the BO is changing as a function of pressure, how the BG is changing as a function of pressure, and how the RS is changing as a function of the pressure. Okay, so just remember, this is an extensive lab, and when you are solving this, when you are working on this lab report, you need to have all the detailed discussions on the theory part, on the experimental procedure, calculation analysis. You need to have these tables. You need to clearly explain at least one series of calculations